Good morning, this is your Stats Sensei, Mr. Spensei, and this is problems 91 through 100 of the death packet. And to be honest, these are probably some of these are pretty challenging. In fact, this first one is very long, and so I've already started it to work it out. So the distribution of weights of loaves of bread for a certain bakery follow a normal distribution. Based on a very large sample, it was found that 10% of the loaves weighed less than 15.34 ounces. All right. And 20% of the loaves weighed more than 16.3 ounces. What are the mean and standard deviation of the distribution of the weights of the loaves of bread? Well, whenever I don't know, I start off with my organizer, z equals x bar minus mu sigma, and I plug in and I go, well, I have 15.34, but I don't know the mean. I don't know the standard deviation. In fact, that's what they're asking me for. But I do happen to have 10%. So the 0.10. So I went to the calculator. I went second vars, inverse norm, zero point 0.1, mean is 0, standard deviation of 1, and I have left, and I get negative 1.2815. So that gives me this, but I'm still missing two things. I'm kind of stuck. So I did the same thing for the other one, but it was the upper 20%. It said weighed more than that. So we're looking at the top 20%. So I went, well, I plugged in my 16.31, and then I went to the calculator and I went second vars, inverse norm, zero point 0.2, and I'm looking for a z-score, so that's why it's 0 and 1. And now I'm working on the right-hand side, and I end up getting 0.8416, and I plug in. Then I recognize, hey, I have two equations and two unknowns. So I can solve this by system. So I reorganize this. So this I just multiplied by the standard deviation. I ended up with 0.8416. I know that's not written very well, so I'll rewrite it. So that's 0.8416 standard deviations equals 16.31 minus mu. And this is negative 1.2815 standard deviations equals 15.34 minus mu. So I have two equations. All right, so then I went ahead and I just stacked those two equations just like that. Well, to combine them, I need to change the signs because I need a variable to drop away, and I'm going to let the mean drop off. So if I made this negative, and this positive, the means will drop off. And when I combine those, I end up with negative 2.1231 standard deviations equals negative 0.97. All right, I'm going to divide both sides by that 2.1231. So negative 0.97 divided by negative 2.1231. Oops. And I end up getting standard deviation of 0.4568. All right, so we know our standard deviation, and really at this point, we actually know our answer, but I'm still going to check it out. Well, we had the equation 0.8416, and I'm going to plug into that. So 0.8416 times 0.4568 equals 16.31 minus mu. So let's check that out. Let's multiply that times 0.8416. And we get 0.38, and then I subtract 16.31 from both sides. You know what? I'll go ahead and start writing this out. This is 0.3845 equals 16.31 minus mu. I'm going to subtract 16.31 from both sides. And now I have negative 15.925 equals negative mu. Well, if I multiply both sides by negative 1, I end up with a positive 15.925, and I end up with my answer choice of D. A lot of work. That's shown up about 3 times in about 25 years. So not that common, but it has shown up. A group of chemistry students debated which fast food chains had better quality backs, fast food chain W or fast food chain M. They decided to investigate by selecting a random sample of 25 bags from each fast food restaurant, slowly adding water until each bag began to leak, and recorded the volume of water they were able to pour into each bag. They then calculated the mean volume and standard deviation in ounces for the two types of bags. Which the following are the correct null and alternative hypothesis? All right. So, and they're looking to see if it is different. All right. So first off, you should never ever use the samples. So that's gone because that's the sample mean. And since it is um, different, we're not looking for a greater than or a less than symbol. And by the way, this couldn't be it because this always has to be equal. These are not necessarily bad choices, except for the fact that we needed it to be different when different means not equal to. So our best choice for problem 92 is E, because it's the only one that had different on it. Normally, I would have done this like this: HO mu W minus mu W equals uh, mu M, and the alternative mu W does not equal mu M. However, you need to be able to recognize it written like this and written like that, both ways. All right, number 93. A random sample of monarch butterflies and a random sample of swallowtail butterflies were selected, and the difference in the average flying speed for each sample was calculated. A two-sample t-test for the difference in means was calculated to investigate whether the speed at which monarchs fly on average is faster than the speed at which the swallowtails fly. All conditions were met, and the p-value was given as 0.072. So which of the following is a correct interpretation of the p-values? All right, p-value is the probability of getting a test statistic this extreme or more extreme given that the null is true. So we have the HO, the mean of the monarchs equals the mean of the swallows. The alternative is the mean of the monarchs is greater than the mean of the swallows. All right, so the probability, that's not it. It's the probability that we'd get a test statistic this extreme. There's a 7.2% chance we get a test statistic this extreme, indicating that the monarchs flew faster when in fact there was no difference. All right. Assuming the monarchs fly at the same speed, on average, the probability of observing a difference equal to or greater than this, that's it. As extreme or more extreme, greater than or more. All right. 94. Tricky problem. As lab partners Sally and Betty collected data for a significance test, both calculated the same Z statistic, but Sally found the results were significant at alpha equal 0.05 level, while Betty found that they were not. Okay, so I'm going to put an S for Sally and B for Betty so we can keep them separate. When checking the results, the women found that the only difference in their work was that Sally used a two-tailed test. All right, so she used a not equal, and Betty used either a greater than or a less than. We don't know which yet. Um, Betty used a one-tailed test. Which of the following could have been their test test statistic? Well, Sally found that it was significant. All right. Which means if Sally found it was significant and she's working with an alpha equal to 0.05, that means the area in the upper tail and the area in the lower tail are 0.025 because this is not equal and this is Sally. All right. So I should be able to find a Z statistic. So if I do a second vars inverse norm, and I take that 0.05 and divide it by 2, and let's go ahead and do center, and we get 2 uh, I should have gotten a Z statistic. What did I do incorrectly here? Second vars, inverse norm, parenthesis 1 minus 0.95, close parenthesis, divide by 2. Let's just do the left-hand side. There, and I get a Z statistic of negative 1.96. Well, it's symmetric, so I could have had a Z statistic of 1.96. For Sally to reject, she'd either have to have a Z statistic greater than 1.96. Well, that doesn't happen, so it can't be that. Or it has to be less than negative 1.96. And the only answer choice is A. But the question is, how did Betty fail to reject? Well, if Betty also calculated a negative 1.96, but said, hey, it was an upper tail test, then her rejection zone is up here. She would have a alpha equal to 0.05, second vars, inverse norm, 0.05. And she has to be on the right-hand side. She would have to have a Z statistic greater than 1.64. Well, Sally rejected, which means she had to have something like this. And a negative 1.98 is not in that rejection zone for Betty. All right. So the only way it was is they had Sally had a not equal, and Betty must have had a greater than test, not a less than, but a greater than test. All right. So the answer choice to 94 is A. 95. Using the same data, one student performed a hypothesis test and where the proportion equals 0.85, and also did one proportion not equal to 8.85. A second student performed the test at 85 and less than 85. Even though both used alpha equal 0.05, the first student claims there is not enough evidence to reject. The second student rejected. Which of the following could have been the test statistic? All right. So, second student rejects. So I need to have something less than 0.05. So let's just say this is my alpha, this is 0.05. And they're going to reject. So they're going to reject with anything less than second vars, inverse norm, make that a left. And the reason it's to the left is because it went this way. They're going to reject with anything less than a negative 1.645. So anything less than negative 1.645, they reject. Well, that gets rid of this one, this one. These two are the same. They shouldn't be the same, but they are. Not sure how that happened. However, the first student had a not equal to, which means they have 0.025 in this tail and 0.025 on this tail. So let's do an inverse norm for that. Second vars, inverse norm, 0.025. We know it has to be left because they rejected. And we end up with a negative 1.96. So the only way they reject is with a negative 1.96. All right. So what I've told other people before in past years that this right here needed to be a positive. So that's why this is gone. And they would have rejected with a negative 2.1, negative 2.3, but they didn't reject. So it couldn't be this one. The only one where this student rejects and this one doesn't is at the negative 1.8 because it's within those two parameters. It's within these two values between those two. 96. Two community service groups, J and K, each have less than 100 members of both groups. Members of both groups volunteer each month to participate in a community-wide recycling day. A study was conducted to investigate whether the mean number of days per year of participation was different for the two groups. A random sample of 45 members of group J and a random sample of 32 members of group K were selected. The number of recycling days each member selected in part and for the past 12 months was recorded, and the means for both groups were calculated. A two-sample t-test for difference in means will be conducted. Which of the following conditions for inference have been met? The data were collected using a random method. We don't know what it was, but they did tell us that, hey, it was a random sample, so we have to accept that one. All right. Each sample size is less than 10%. Well, if I go 45 times 10, that equals 450. And they told us the population size for each group was 100. This was not met. The other one was 32 times 10 equals 320. Both of those are greater than the 100 group size. So that one's not met. Each sample size is large enough to assume normality. N equals 45, greater than or equal to 30. N equals 32, greater than or equal to 30. Both are large enough to assume normality. So in this case, 2 wasn't good, but 1 is and 3 is. So our answer choice for 96 is D. 97. Researchers studying two populations of wolves conducted a two-sample t-test for the difference in means to investigate whether the mean weight of the wolves in one population was different from the mean weight of wolves in the other population. All conditions for inference were met, and the test produced a test statistic of 2.771 and a p-value of 0.01. All right? And they said was different. That means we're looking at a not equal to, we're looking at a two-tail. What is the correct interpretation of the p-value? The probability of a p-value is the probability of getting a test statistic this extreme or more extreme given that the null is true. Well, what would our null be? Well, in this case, HO, mean of 1 equals the mean of 2. HA, mean of 1 does not equal the mean of 2. So basically, the null is that there's no difference in weight. So given that there's no difference in weight, there's a 1% chance we get a test statistic this extreme or more extreme. So for 97, assuming that the mean weights of the population are equal, all right, the probability of obtaining a test statistic that is greater than 2.771 or less than this is 0.001. All right. And remember, it has to, because it's two-tail, we have to address both tails. And that's the problem with part A. Part A only addressed one tail, or question answer A only addressed one tail. Our best answer choice for 97 is E. All right, 98. A company director investigated whether there's a difference in the mean number of overtime hours worked for each week by employees assigned to two different managers. Each manager, A and B, manages 100 employees. Random sample of 35 employees from manager A and 40 employees from B were selected. The number of overtime hours were recorded for 75 employees each week. Have the conditions been met for inference? No. All right. And it's like, oh, they took a random sample. Yay, they did that. So random sample is met. N is less than 10%. Well, 35 times 10 is 350. That's greater than 100. 40 times 10. Well, 35, our sample size times 10 equals 350. That's greater than 100. That's a fail. And a 40 times 10 equals 400. And that's greater than 100. So it failed on the N is less than 10%. No, because the size of at least one of the samples is greater than 10% of the population. All right. Sample sizes were large enough, but the problem was in this case that they did not meet the N is less than 10%. So there, which struggles with independence. A study was conducted to investigate whether the mean number of snack bars at two airport convenience stores, C and D, were different for 10 randomly selected days. The number of snack bars sold at each store was recorded, and the sample mean number of bars for each store was calculated. A two-sample t-test for difference of means will be conducted. Have all the conditions been met? All right. So we have 10 days. So in this case, our sample size for both stores is 10. In order to meet normality, this had to be greater than or equal to 30. So normality was not met. So the sizes are not large enough to assume normality because our sample size was too small. We needed to have 30 days or more. All right. So we needed to have, instead of 10 randomly selected days, we had 30. They were random. That was good. But we don't have the right size uh, sample in order to be normal. It's also possible that there weren't enough snack stores either, but we don't know that. For a population of leghorn chickens, the mean number of eggs per chicken is 0.7. All right. So the mu is, and this is for leghorn, mu L equals 70.70 with a standard deviation 0.2. For a population of Sussex chickens, the mean number of eggs laid were 0.5 with a standard deviation of 0.10. Two independent random samples were taken, and this is the information that was found. So here's our sample means, there's our sample standard deviations. Mike claims that for all samples of size 36 from the population of leghorn chickens and all samples of size 36 from the Sussex chickens, the mean of all possible differences minus is 0.3. And what he did was he went this times this and got 0.3, which seems reasonable, except he said for all samples. And the mean of all samples, the mean is the mean is the mean. The mean will be the population mean. So this is what he did. That's incorrect because we needed to be looking at the population mean. And the population mean was 0.7 minus 0.5. So our answer choice is C for 100 because we need to be looking at the true population. Because if you did enough of them, any sample can vary from the true population, but if you do enough of them, you should equal the true population, and these are the true population values. All right, this concludes the death packet. Appreciate you watching. Look forward to seeing you on the next one. Thank you.